So we spent all this time, all this compute, obsessing over hyperparameters, right?
Yeah.
Learning rates, weight decay. We just assume the model is meticulously learning from the data.
We do.
But this new paper from the Falcon LLM team, it basically suggests we've been fooling ourselves. It seems our models haven't actually been learning the scale of their own weights.
No, they've just been stuck. It's a kind of physics trap.
A physics trap. They call it the noise WD equilibrium, right?
Exactly. It's a really elegant idea when you break it down. You've got two forces. First, you have the stochastic gradient noise, which is always trying to, expand the weight matrix.
Like a gas expanding. A Brownian motion.
That's a perfect analogy.
Yeah.
And then you have weight decay, which is the counterforce, always trying to crush everything back down to zero.
And we thought that was a healthy balance. But what they're saying is it's not a balance, it's a stalemate. The scale of the matrix, its norm, it just stops changing based on the data.
It just becomes a function of your hyperparameters, the learning rate and the weight decay.
So the loudness of a layer has nothing to do with how important that layer is for the task.
Nothing. It's just determined by the random physics of your optimizer settings. The model is structurally unable to decide, say, that layer 4 needs to be louder than layer 5.
That is wild. They're all just stuck, floating in this predetermined state. Okay, so how do we get them unstuck? This is where the learnable multipliers come in.
Yeah, the LRMs. And the idea is actually, it's deceptively simple. You just decouple the magnitude of a layer from its direction.
So you let the huge weight matrix keep doing its thing, learning the directions, which features map where.
But you introduce a separate tiny little parameter that only handles the scale.
And that can be just a single number, a scalar, or a vector for rows and columns.
Right.
But here's the part that I had to really think about. If the whole matrix is stuck in this noisy equilibrium, why isn't the tiny multiplier stuck too?
That is the core question. And it all comes down to the signal-to-noise ratio. That main weight matrix is huge, right? The gradients coming back to it are incredibly noisy.
That's the stochastic part of stochastic gradient descent.
Exactly. The Falcon team actually showed that the matrix updates are noise-dominated. They look just like random simulations. They aren't learning scale at all.
But the multiplier, because it's just one number, it's signal-dominated.
Precisely. The noise just averages out over the whole batch, and you're left with this pure, strong gradient signal. So while the matrix is stuck fighting itself,
The multiplier just calmly listens to the data and adjusts the scale. It frees the scale.
that's the phrase they use. And they proved it with that projector experiment, which was just brilliant.
Oh yeah, tell us about that. They took the final layer, the one that maps to the vocabulary.
And they tried freezing its scale, and the results were catastrophic. The model just couldn't converge properly. But the second they added the learnable multiplier,
Performance snapped right back.
snapped right back. It proved the model wants to adjust these scales. It's desperate to, but the training dynamics just won't let it.
Okay, let's talk benchmarks. Because this is all great in theory, but they ran a big 200 gigatoken training run.
And this is where the implications get really interesting. Just adding these simple multipliers to a model training with Adam,
Yeah.
it gave a performance boost of about 1.2%. Now, that might not sound like a lot, but that is almost the exact same gain you get from switching from Adam to the much newer Muon optimizer.
Wait, really? So just fixing the scale on good old Adam basically catches it up to Muon.
It suggests that a huge part of Muon's advantage might just be that it handles the scale problem better. We might be getting to the same place, but through a much, much simpler path.
And the gains weren't even, were they? I remember the paper said it was much better on certain tasks.
That's right. The improvements were way bigger on reasoning tasks, so math, logic, that kind of thing, than on simple knowledge recall.
Which makes sense when you look at the other thing they found, layer diversity. Once the multipliers were in, different parts of the model started to adopt wildly different scales.
Yes, standard training kind of forces every layer to have roughly the same scale. But with multipliers, the MLP blocks, for example, suddenly grew much, much larger than the attention blocks.
So reasoning requires some layers to shout and others to whisper.
It seems so. It needs that hierarchy, that heterogeneity, which standard training was suppressing.
And you get all of this flexibility with almost no extra memory, no hit to inference speed. It really does feel like a universal patch.
It does. It works on Adam. It works on Muon. It feels like it fixes a fundamental problem we didn't even fully realize we had.
It really makes you wonder then, if our model's reasoning skills depend on this kind of flexible internal scaling, and we've been accidentally clamping it down this whole time.
Have we been hamstringing our model's ability to think just to keep the training stable?
That's the uncomfortable question. And if the scale of our weights was just a harmful artifact of training noise, what other parts of these giant networks are just noise masquerading as intelligence?
Something to think about.
Definitely something to think about. Thanks for listening to this deep dive.
Until next time. So today we're doing a deep dive into a really fascinating paper from researchers at Meta AI and Carnegie Mellon. It's about a system they call FusionRoute. And honestly, it gets right to the heart of what I'd call the Goldilocks problem in AI right now. You have these absolutely massive generalist models, your God models.
Right.
They can write poetry, they can do calculus, but they just burn through money and compute. They're just too big.
Way too big. And then on the flip side, you've got these little specialized models, a math whiz, maybe a coding bot.
They're too small.
Exactly. They're cheap, they're super fast, but they are so narrow. You ask that math bot to write you a poem and it falls apart.
So the big race has been to figure out how to get that massive God model performance, but by using a team of these smaller, cheaper experts.
And that's where FusionRoute comes in.
Right. But to really get why it's so clever, we have to talk about why the old ways of doing this, like model merging, just don't really work.
Oh, it's a huge problem. You can't just smash two neural networks together.
It's not that simple, is it?
Not at all.
Yeah.
You run right into this thing called parameter interference. I mean, if you literally average the weights of a math model and a language model, you usually get a new model that's just bad at both.
Huh, yeah.
The paper's analogy is great. It's like trying to make a super driver by combining a Formula One racer and a taxi driver.
Yeah.
You don't get the best of both worlds, you just get a mess.
A total mess. Okay, so then you have what they call sequence-level collaboration.
Which is basically a committee meeting, right?
Yeah. You ask a question, and every expert writes a whole essay, and then some other system has to pick the best one.
It can work, but it's just so inefficient. You're running 5 models just to get one single answer.
So that brings us to what FusionRoute does, which is token-level collaboration. And this is the key insight, I think.
It really is. It's not about switching experts for a whole sentence or a paragraph.
It's switching per token.
Which, for anyone listening, is essentially a word, or sometimes even part of a word. It's incredibly fine-grained.
The paper breaks it down into 2 steps. First, there's selection. That part seems pretty intuitive. If the next word looks like Python code, you just point to the coding model.
Right. If it's a number in an equation, point to the math model.
But the second part, complementation, that's where they say the real innovation is.
This is the breakthrough. Because in older systems, the router, the thing directing traffic, it was passive. It would just say, okay, math expert, it's your turn. Go.
And it just had to trust that the expert was right.
Blindly.
Yeah.
And the problem is, what happens if that math expert is really confident but totally wrong? The system had no way to correct it.
I see. So FusionRoute changes that.
It does. The router here isn't just a traffic cop. It actually generates its own complementary logits.
And logits are basically the raw probability scores for what the next word should be.
Exactly. So think of it like a driving instructor. Selection is letting the student drive. But complementation is the instructor keeping their hand right next to the steering wheel. If the student starts to drift, even a little bit,
the instructor can nudge it back on course.
yes. Without having to grab the wheel and take over completely, it just applies a little corrective pressure.
I thought the theoretical proof they had for this was so cool. They actually showed, mathematically, that just picking the best expert isn't enough.
Because sometimes none of the experts have the perfect answer.
Right. You absolutely need that outside signal, the instructor's nudge, to bridge the gap. That's the real aha moment.
It lets the whole system become, greater than the sum of its parts.
So to make this work, they needed a special training method, they call it, CDPO, Complemented Direct Preference Optimization.
It's a mouthful. But the gist of it is that it specifically trains the router on when to step in.
You don't want the instructor grabbing the wheel all the time.
No, that would defeat the whole purpose. CDPO teaches the router to recognize those specific moments an expert is likely to fail, and only then does it apply its own corrective nudge.
And the results seem to back it up. Looking at the benchmarks on Llama 3 and Gemma 2, it beat model merging and standard fine-tuning across math, coding, you name it.
It did. And what's really neat is that for a user, this is all invisible. You don't have to click a math mode button. The system just adapts on its own, token by token.
It really does shift the narrative, doesn't it? We've been so obsessed with these scaling laws, the idea that you just have to make models bigger and bigger. But this suggests you can build these incredibly powerful systems from smaller, cheaper parts
Yeah.
if the coordination is smart enough.
It almost democratizes high-end performance. You don't need a billion-dollar data center if you can get small, efficient models to work together this well.
It's like a hive mind, which I guess leads to a final thought. If we can get small models to correct each other's mistakes word by word like this, to perfectly finish each other's sentences, does the future of AI look less like a single giant superbrain and more like a collective consciousness of specialists all talking in perfect sync?
Something to think about.
Well, that's it for this deep dive. Thanks for listening. It's pretty rare you see a company stare into the abyss and, actually manage to pull itself back. I mean, 2 years ago, that huge joint venture between Hyundai and Aptiv was effectively dead in the water.
It really was. They'd missed their big launch with Lyft. Aptiv had just pulled its funding.
And then they slashed, 40% of their staff just last year? It looks like the end.
A classic evolve or die moment. But according to this great piece we're looking at from TechCrunch by Kirsten Korsak, they chose evolve.
A total reboot.
A total reboot, yeah. And now they're aiming for a fully driverless service in Las Vegas by the end of 2026.
And this isn't just some press release fantasy, right? Hyundai stepped in with $1 billion to back this up.
$1 billion. But the money isn't even the most interesting part of the story.
No, the real story here is the pivot in their engineering. They've fundamentally changed how the car thinks.
Right. This is the big shift from what we could call classic robotics to a new AI-first approach. And to get why that matters, you have to understand why the old way failed.
So classic robotics, that's what the industry has been stuck on for years, right? Where you kind of compartmentalize everything.
Exactly. You have one piece of software that detects a pedestrian, another that predicts their movement, and a third that decides how to steer.
It's all modular and relies heavily on hard-coded rules. If this happens, you do that.
The problem is you can't write a rule for every single weird thing that happens on a city street. It just doesn't scale. It's too brittle.
So Motional threw that out.
Pretty much. They're now using what they call an end-to-end foundation model.
And this is where the comparison to something like ChatGPT is actually pretty useful because they're using the same underlying architecture. Transformers.
But for the physical world.
Yeah.
So just like a language model predicts the next word in a sentence, Motional's model predicts the next few seconds of driving.
So it's not following a rule book. It's learning behavior from, I assume, massive amounts of data.
That's it. And that solves the scaling problem. The CEO, Laura Major, made a really key point about this.
Oh, about moving between cities.
Yes. In the old model, if you moved a car from Boston to Vegas, you might literally have to rewrite code because the traffic lights look different.
That sounds incredibly inefficient.
It's why AV expansion has been so slow and expensive. With this new model, you don't rewrite code. You just feed it data from the new city, it trains, and it adapts. It learns to generalize.
Okay, that's the theory. But let's get to the reality check. The TechCrunch reporter, she actually got in one of the cars.
She did. A Hyundai Ioniq 5 in Las Vegas to test this new brain.
And she didn't pick some easy suburban loop. She went right for the chaos of the area hotel pickup zone.
Which is a complete nightmare. I mean, it's not a normal road. You have tourists just wandering into traffic, taxis cutting everywhere.
And there was this one moment the article highlighted boss battle, they called it.
Ah, the Amazon van.
The double-parked Amazon delivery van.
Yeah, and this is the perfect stress test. A rules-based system would just hate this. The van is blocking the lane, but not all of it. Is it stopped? Is the driver out to jump out?
There's no clean rule for Amazon van half blocking the lane while a tourist takes a selfie.
Exactly. So what did the AI do?
It hesitated.
And that's the key word. It didn't freeze. It paused to process the context, kind of like a human would, and then it just navigated around it.
Zero human intervention, no disengagements.
That one maneuver basically validates the whole billion-dollar bet. It proves the new approach works in a complex, messy environment.
So looking ahead, they have this employee-only service running now. It opens to the public later this year with a partner.
And then the big goal. Pull the safety drivers out completely by the end of 2026.
But there's a bigger play here, isn't there? Hyundai isn't dropping all this cash just for a small taxi fleet in Vegas.
Not at all. Laura Major was very clear about this. Robotaxis are just stop number one.
The real goal is level 4 autonomy in consumer cars, the car in your driveway.
Exactly. The economics of the old classic robotics would never work for a personal car. It's too much specialized hardware, too much maintenance.
But if you have a foundation model that just learns and gets better with data,
Suddenly, it's more of a software problem than a hardware nightmare. It brings the cost way down.
If the model holds up, of course.
Well, that's the billion-dollar question.
I mean, we have spent years in this pilot purgatory because the tech just couldn't handle the real world. But if Motional's right, and the answer isn't more rules, but better learning,
Then we might finally be moving past the era of endless pilot programs.
we'll have to see what happens in 2026. Thanks for listening to this deep dive. So, for what feels like a decade now, the formula in Silicon Valley has been almost painfully simple. If you want a smarter AI, you just build a bigger one.
Exactly. More data, more parameters, more compute. It's what's known as the bitter lesson in computer science.
Bigger lesson.
The idea that brute force just, well, it always wins over trying to be clever with algorithms.
But that's why we're doing this deep dive. We're looking at Sara Hooker's essay, The Slow Death of Scaling, and her argument is that this entire era, it's ending.
And it's not just a theory. The data is really starting to show it. That neat correlation between model size and, intelligence.
It's breaking down.
It is. We all used to just assume you needed a Goliath like GPT-4 to get the best results. But that's not what the benchmarks are saying anymore.
It's this David versus Goliath thing happening, isn't it? You see a model like Llama 3.8b or Command R35b.
Tiny, relatively speaking.
Tiny. And they're outperforming something like Falcon 180D.
Which proves that parameter count is, well, it's becoming a vanity metric.
The one that really got me was the Aya 23 model. It beats Bloom, which is this 176 billion parameter beast. And Aya has, something like 4.5% of the parameters? I mean, that just shouldn't be possible if the bitter lessons still held.
Well, it's possible because we're realizing deep neural networks are actually incredibly inefficient learners.
Inefficient how?
They need a staggering amount of compute just to learn the rare stuff, the long-tail concepts. And for years, our solution was just to make the net wider. It's wasteful.
Which brings us to this redundancy paradox. We spend millions training these huge models.
Millions. And megawatts of power.
And then researchers discover you can just, prune away most of the weights after training, and it barely affects performance.
It forces you to ask the question, right? If you could just delete them later, why did we burn all that money and energy training them at all? It suggests our whole method is a bit crude.
It reminds me of the invention of the microwave. The original tech, the magnetron, it was for WWI radar. It was massive, brute force military hardware.
All about raw power.
Exactly. But it took that one engineer with a melted chocolate bar in his pocket to realize you could use that same tech for something smarter, smaller, more efficient.
That's a perfect analogy. AI is moving from the radar station era to the kitchen counter era.
You don't need a skyscraper to house intelligence. But Hooker makes a really important point here about the environmental side.
The Jevons paradox.
Right. Just because the models get more efficient doesn't mean we use less energy.
No, because if they're cheaper to run, we'll just use them in 10,000 more places. So we can't just get smaller, we have to get smarter.
And this is where the new levers of progress come in, like malleable data space. We're finally getting past the idea of just, dumping the whole internet into a model.
We have to. The more data pipeline is hitting a quality ceiling. So now it's all about synthetic data, about aggressive pruning. It's like reading one perfect textbook instead of the entire messy Library of Congress.
You get a smarter result in less time. Okay, but the other lever, and I think this is the really radical one, is inference time compute.
This flips the entire economic model of AI on its head.
How so?
For years, all the money went into training. Now, the focus is shifting to spending resources when the model is actually being used.
So it's like giving the AI a moment to think.
Precisely. It's System 2 thinking. Instead of a gut reaction, techniques like chain of thought let the model work through a problem. You don't always need a bigger brain. Sometimes you just need more time.
And that changes the whole playing field. If you don't need a billion-dollar supercomputer anymore, if all you need is smarter data and better inference.
The moat around the big tech labs starts to disappear. It could democratize the whole field.
Yeah, innovation moves from a handful of rich labs to anyone with a great idea. It's a shift from brute force to elegance.
It really is.
So here's the final thought for you to chew on. If the next huge breakthrough doesn't require massive scale, who's out there right now in their garage using these smaller, smarter tools to build the thing that makes today's giants look like dinosaurs?
That is probably the most exciting question in all of tech right now.
Thanks for diving in with us.